Hi, everybody. This is the notes for, excuse me, 4.1, which is the beginning of solving systems of equations. The first method we're going to use to do this is graphs, which we just were working with in chapter 3. So a system of equations by definition is two or more linear equations together. So when they're graphed on the same coordinate grid, the solution is an ordered pair, it's a point, that is on both equations. So when we find an ordered pair solution, it's an x point or an x value and a y value. It's always 2 because there's an x and a y in each equation, okay? And it is going to be when I have 2 lines on the graph. Actually, we'll see that in a second. I'm getting ahead of myself. So if a system of linear equations has one or more solutions, which means if I think about my graph and I have 2 lines on it, I have line this way, I have line this way. It's consistent if it has a solution, which means it crosses at least one point. This is a consistent system. When a system of linear equations has no solution, it's inconsistent, okay? So it means that there's 2 lines and at least 2 lines and nothing touches anything ever, okay? If 2 equations represent the same line, all the points are said to be dependent equations. Essentially, if you go to graph and you graph the same line twice, these systems are dependent. All points on the line are solutions. It means that I did my graph and I had this equation and then I had the same one come right over top of it. Same line twice. No matter what point you pick, they're all on both lines. If 2 equations represent 2 different lines, they're independent, okay? So again, like my first example, I had line this way, I have this way. As long as they're not right over top of each other, at this point, independent equations either intersect at one point or are parallel. And if we go back a step, this is a consistent system. They intersect at one point. An inconsistent system is when 2 lines are parallel. They're never going to touch. Okay, so the first step here is determine whether an ordered pair is a solution to the system. And the way we do this is we take this point, 3, 1, and we put it in where we see x and where we see y for both equations. We put it in both. We don't just do one because it might not work in both. And for it to be a solution, it has to work in both places. So I'm going to do 3 plus 1 equals 4. And -2 times 3 plus 1 equals 4. Well, 3 plus 1 is 4. That works. -2 times 3 is -6 plus, oops, sorry, I don't know why I wrote 4. It's -5. That's what the problem is. -6 plus 1 is -5. Check. So in this case, 3, 1, the answer is yes, it is a solution. Let's try this one. We do the same thing. So we do 0 plus 4, because that's x and y, equals 4. That's true. And then we have -2 times 0 plus 4 equals -5. Well, -2 times 0 is -4. 4 is never 0. Pardon me. I have like an itchy throat today. And then 4 does not equal -5. So this is not a solution. So the answer here is no, not a solution at all to this pair. You can try these two. So take a minute and see if they work for you. Put in this point, 6, 3 into both equations, and then do the same for 4, -2. I will tell you that 6, 3 does not work for both, and 4, 2 does. Okay, so now, me and my scratchy throat are going to talk through the rest of this. Hold on. Forgive me. All right, so there's a couple of different ways that solution sets of systems can work. The first is there's one unique solution. When this is the case, there's one point of intersection. The system is consistent and the equations are independent. Those are those words we saw earlier. When there's no solution, these are parallel lines. The systems are inconsistent because they never cross. And the equations are independent because it's two different lines, okay? And then the last case is that there's infinitely many solutions. Every point is a solution. These are what's called coinciding line, and that's going to be a new term. You're going to hear it. Coinciding lines are just the same line over top of each other. The systems are consistent and the equations are dependent because they're the same. So what we're going to do is we're going to start solving. So we're going to solve the system by graphing. So we're going to graph each equation. I'm going to do that one in red. Y equals 2x. I know the slope is 2 over 1 and the y-intercept is 0. So I'm going to graph. Point at 0, up 2 over 1, up 2 over 1, down 2 over 1, down 2 over 1. When we're graphing like this, it makes sense to make lines, take up some space so we can find where they cross. You don't want to not have drawn it far enough and not know the solution as a result. And then y equals 2. So when y is 2, at every x value, y equals 2. Okay, so let me actually put that in another color. There's my second line. Okay, and for me, what matters is where they cross. And if I had drawn my graph better, they would cross right here. Okay, so the point of intersection is 1, 2. And what I can do is put those into the graph to the equations and see if it works. Well, when y equals 2, x2 equals 2 times 1, that definitely works. And then 2 equals 2, that also works. So this is the solution. That's how you check. You try this one. Graph -3x, or y equals -3x, and then graph x equals -1. So for y equals -3x, m is -3 over 1. Y-intercept is 0. And let's do that one first. So I'm going to start here. Down 3, right 1, down 3, right 1, up 3, left 1. Approximately my line. And x equals -1 is a vertical line at x is -1. Okay, so you can see where they cross. They cross here. That is at -1, +3. And if you want to see if that works, plug them back in. So for this guy, y is 3 equals -3 times -1. Yep, that works. And then -1 equals -1. Well, that's true. So this guy works out. Now, it's not going to be that simple forever. Let's do something a little more complicated. In this case, what you do is you're going to graph. And clearly my little graph is covering up my words. So what I am going to do most often is I'm going to look at these equations and think about how to graph them first. So I'm going to put them in y equals mx plus b, just because that's an easier way for me to handle this, right? So I'm going to transform them. I'm going to start by moving x. So I'm going to get -2y equals -x minus 2. I divide everything by -2. And so I get y equals 1/2 x plus 1. All right, we'll make that the blue one. This guy, 1/2 x is up 1 over 2, and the y-intercept is 1, 0, or 0, 1. So let's see, from there, I'm going to go up 1 over 2, up 1 over 2, down 1 over 2, down 1 over 2. So there's my first line. There's the blue guy. I'm going to do the same thing to the second one. So I'm going to add 3x to the other side. So I get 2y equals 3x plus 6, divided by 2. Y equals 3/2 x plus 3. All right, so the y-intercept's at 3. 1, 2, 3. And we're gonna go up 3 over 2. Maybe I'll go the other direction. 1, 2, 3. Up. And there we go. So sometimes you have to experiment a little bit to figure out where they're going to cross. In this case, they're going to cross at -2, 0. And you can and should check yourself to make sure it's right. This one is. Okay. All right, you try this one, pause the video, do the same process. All right, so I will tell you the first equation transforms. We don't need to transform. We already see it. It's already in the right form. So the slope is 2 over 1. The y-intercept is 0, -3. So let's see, 0, -3. Up 2 over 1. 2 over 1. 2 over 1. There's my line. The second one I do need to transform. Let's do that in another color, -6x. I get 2y equals 4, oops, sorry. 6, -6x plus 4. Divide everybody by 2. I get y equals 3, -3x plus 2. Okay, so in this case, the y-intercept's at 2, 0, or 0, 2. Boy, I'm backwards today. And down 3 over 1. Huh. Our line works out right away. So now we can see that point is at 1, -1. And you can check that in your equations to see if it's right. Let's try another. All right. Same ideas, okay? So I'm going to transform the first one over here. I'm going to add x to both sides. It's going to give me 3y equals x minus 6 divided by 3. So I'm going to get y equals 1/3 x minus 2. All right. Starts down here. I'm going to go up 1 over 3. Up 1 over 3. All right, that's about my line. And then let's try this one. Everybody gets divided by 6. I didn't have to move any x's, so I get y equals 1/3 x plus 1. So what I see right here is these guys have the same slope, but they don't have the same y-intercept, and that's going to be something you notice eventually. So I'm going to see this guy goes at 1. He goes up 1 over 3. Up 1 over 3. What this system is inconsistent. These are parallel lines. So there is no solution here, and that is what you need to tell me. No solution. Inconsistent. Ooh. Okay, you need to tell me that you know what's happening here. That's part of your job. All right, let's try another. All right, you graph. See if you can get it to work. I will tell you that once again, here there is no solution. You should get 2 parallel lines that are inconsistent. If you don't, come on into the discussion and let's talk about it. All right, one more kind of thing. So let's try this. Same as before, I'm actually going to do the easier one first because that one's already done. So I have -1/4 x plus 2. So the intercept is at 2. And it's down 1 over 4. Up 1 over 4, kind of looks like that. And then I'm going to transform the other one. So minus x to both sides, I get 4y equals -x plus 8. Divide everybody by 4. I get y equals -1/4 x plus 2. That's the same as this guy over here. So actually, it's the exact same line right over top. Same y-intercept, same slope. So that this means that these are, there's infinitely many solutions. Which is a word I can't spell. Infinitely many solutions. These lines are dependent. Okay. The other word we can use is this word we saw earlier, which is coinciding. These are coinciding lines. Okay, but it's some way, shape, or form. You need to tell me you know this, okay? All right, and this last one, this is gonna work out the same way. These guys are also gonna be coinciding. See if you can figure out how that works, okay? If you can't, come into the discussion. Let's talk about it. All right, this is the end of 4.1. Move on to what's next. Stick with the PICE and the module.